Okay, so welcome everyone to this first Graviticulous seminar of this semester of 2022. Today is the time of Gorazd Cvetic. He has a PhD in Cornell University, and since 2000 he's a professor at Universidad Técnica Federico Santa María in Valparaíso. And this talk is based on the ongoing work in collaboration with Diego Teca and César Ayala. So please, Gorazd, go ahead with your talk.
Yeah, thanks. Thank you very much for the introduction. I will be talking about the work that I'm doing with César Ayala y Diego Teca in Santa Maria in Valparaíso. It's continuation of our work, which was published until now in 2 papers. And what I will present now, in fact, is new. Yeah, has not been presented yet. There are some improvements in our calculation, and we do get now somewhat different extracted values of alpha S. We use the ALEPH collaboration data for semi-hadronic tau decays, strangeless, that is strangeless hadron production, with cutoff of the square of the invariant mass at 2.8 GeV squared. It's not up to mass of the tau squared, which is roughly 3.1 GeV squared, because we eliminate the last 2 beams of large sigma, which have large uncertainties due to some experimental problems there. The weight functions in the sum rules will be Borel-Laplace weight functions pinched, and an additional filter in our analysis will be finite energy, the usual finite energy sum rules, which are momenta, specifically 2 momenta, A20 and A21, both doubly pinched, these 2 means. The quark-hadron duality violation will be suppressed by the fact that the weight functions are doubly pinched in the Minkowskian part, that is, the part where these duality violations occur. For the theoretical expression of the sum rules, we will use improved version of the truncated operator product expansion for the Adler function. Adler function is a logarithmic derivative of the quark current correlator for U and D quarks. The dimension 0 part, thus we will use this Adler function, whose higher order expansion coefficients are predicted by the structure, by the known structure of the leading infrared and ultraviolet renormalons. So higher expansion coefficients are not known explicitly, but will be estimated with this structure. The lower coefficients are known explicitly and are taken into account up to alpha to the 4th power, and another estimate up to alpha to the 5th power. The dimension 4 term has the known structure, simple 1 over q to the 4th, or q square, while dimension 6 operators in naive form in operator product expansion are this form, but they will be replaced, in fact, by the terms which have specific powers of the running coupling in it, which is now theoretically it's known, these powers there, they are non-zero. So those terms, dimension 6 terms, are more complicated, and we will take them into account now. In the evaluation of dimension 0 part of the sum rules, we will apply basically 2 methods: truncated fixed order perturbation theory and Borel resummation, which is inversed Borel integral with the principal value recipe in specific truncated form. Now, for each truncation index in this method of the D0 part evaluation of the sum rules, for each case of truncation index, we will extract a certain value of alpha S by confronting the theoretical expressions with the experimental ones. And basically, the fit will be done with doubly pinched Borel-Laplace weight functions. And the best truncation index in this method will be inferred from the consideration of this FS finite energy sum rule momenta, namely where the variation of truncation index does not change or change very little this momenta. This in fact is connected with our tau decay ratio canonical value. The averaged extractive value of alpha S will then be presented. Now, concerning the sum rules, the general approach here will be the use of the Adler function, which is logarithmic derivative of the quark current polarization function. Quark current polarization function is a function which appears in the UD bar quark current correlator. Okay, without this tensorial part. Now, one part of this function can be neglected, axial part for g equals 0, because the masses involved in these currents are very small, d and u. This is well known. So there are v and a part of j equal vector and axial vector parts of the current correlator. We will look at the entire this channel, the full vector and axial vector channel for currents, and using v plus a, this entire data of ALEPH. The other thing to notice is that according to the general principles of quantum field theory, this correlator function and thus also the Adler function are holomorphic or analytic functions of q squared. Q squared is this minus q small squared, where this q small is momentum transfer during the decay of tau lepton, semi-hadronic decay. Well, it turns out that these are now functions which are holomorphic. That is, there are no singularities there. We can infinitely many times make derivatives there and consider this q squared now to be complex, in the complex plane now. The exception of this holomorphic behavior is the negative axis. That is where q small squared is positive, which means this is the production channel there. If we have another arbitrary holomorphic function gq squared, we can apply the Cauchy theorem thus to such integral, because this is again holomorphic function in the complex plane with the exception of the negative semi-axis, and along a closed path in the complex plane. For example, if this is q squared plane, this is the semi-axis where singularities may occur in the integrand, but if we integrate around this, we should get 0 by Cauchy theorem. So using this, and this is sigma maximum, this mentioned 2.8 GV squared, we obtain Cauchy theorem, which then gives us this part equal to negative of the this part, and this part on the large contour, we use theoretical expressions, while this part along the negative axis, we use experimental data, namely omega experimental is discontinuity along the negative axis for the correlator, and this is being measured, has been measured with high precision with the, by ALEPH collaboration. This spectral polarization function is basically proportional to this decay widths of tau into semi-hadronic decay widths in specific small integral interval beams, while sigma is mass invariant mass squared of the hadrons produced in certain small intervals. So this is measured, and this will be theoretical. Here we will use all this machinery of operator, product expansion, etc. Now this part on the circle of radius sigma m contour of 2.8 can be transformed by integration by parts, and where d is the logarithmic derivative of this, and now this g weight function that is an arbitrary weight function, almost arbitrary, gets replaced by another weight function, which is integral of this small g. So these are the weight functions of the sum rule, and this g and large g are related. This is Adler function. He will use operator product expansion, and here the experimental values along the entire cut. What else could be said here? Okay, for the moment, no. The quantity omega sigma that is here on the left-hand side is well measured, as I said, by ALEPH for the entire sigma interval, almost up to mass of the tau lepton squared, but the last two beams here have large uncertainties. So what we will cut, as I mentioned, at 2.8 GV squared, we will not take into account the last two beams because of large uncertainty. So up to here, we will take all the sigma, which means this sigma m here and here is 2.8 GV squared, 2.8 roughly here. Now the theoretical operator product expansion of the polarization function, that is of the current correlator, quark correlator, is usually, that is used usually in the literature, has this following form, which is a naive form, dimension 0. These are higher dimension terms, and this is a simple logarithm. The corresponding Adler function, which is derivative, it has no renormalization scale dependence because it cuts out. So this is kind of a quasi-observable, independent of the renormalization scale and scheme. And but it is space-like quantity, not the usual time-like quantities like decay widths or cross sections. Anyway, this Adler function has dimension 0 part, which is pure powers of coupling A. Just to remind you that absolute value of q squared in this integral will be 2.8 GV squared. So we could apply here perturbative QCD. It's not so small, this sigma m here, 2.8 close to 3 GV squared, but it's on the limit between perturbative and non-perturbative. So here we could play with this, and these are higher dimension terms. The naive version, I say naive, why? Let's see. The theoretically better motivated operator product expansion of Adler function is the following. Up to the, well, there is no dimension 2 terms because the masses of U and D quarks are negligible contributions that give us dimension 2. Dimension 4 is remains this naive form. In fact, if we go beyond large beta 0 approximation, it remains like this. This O4 is in fact gluon-gluon condensate, and here it does not run. Of course, we have here 1 plus other alpha s, or A. A is for us alpha s over pi. So in first approximation here we put just 1, no connections with alpha s. But dimension 6 term is more complicated, in fact. It has some condensates of dimension 6 combined with the coupling. This A is alpha S over pi. Okay, it's just couplant, sometimes they call it.
Gorazd?
Powers. See, yes?
Sorry, I would like to, is it possible if you can go back to explain the connection of this, for instance, this Adler function with the Q squared with the tau decay semi-hadronic process that you are looking at? Because I got lost in I don't see the connection between the processes that you are looking at and the tools that you are using.
Yeah. Here, the relation will be this one, basic relation. This is the theoretical part, which involves a contour integral of this Adler function, which is derivative of the polarization function of the current correlator with certain weight function here, along the contour of radius 2.8 GV squared. While these here are the experimental data integrated over all these invariant masses. Now this is measured by ALEPH collaboration. It's polarization function, which is basically, we could say that d sigma times omega experimental sigma is something proportional to QCD part of the decay width of tau into hadrons, such that invariant mass squared of hadrons is in the interval between sigma and sigma plus 2 sigma, something like this. Now, don't ask me too much because I don't know exactly. This is not exactly tau decay width in this interval, but proportional. It has to be rescaled to get this omega here. And they present it also in this form. Why are rescaled? So that this omega is in fact imaginary part can be expressed as this discontinuity part of the current correlation function along its cut axis. Yeah, this axis here, the only part where correlator or polarization function has discontinuity. It has a jump here, and this omega is in fact jump over this. Yeah. Now, the dimension 6 part is in fact not as naive as turns out to be here for dimension 4, which is correct. Here, there are certain powers. In fact, it's even more complicated than that, as these people have pointed out and calculated dimension 6 operators for the V plus A Adler function has 10 different operators. And then they looked at how they depend on ultraviolet cutoff, RGE, the equations for all these operators, and they mix. So they diagonalized this kind of mixing, eliminated the mixing, and they obtained 10 different operators, each with which appears here with its own power of k in OPA, 10 different. However, the first two have almost equal k, the second two has almost equal k, and then it turns out that the other 6 have these powers even higher. This is high. Okay, sorry, this is the lowest, 0.22. This is already considerably higher. And the next one has powers already close to A to the second power, etc. So they are expected to be suppressed. So what we do is we take the first two powers that are almost equal for the two, we put them together, roughly this. And the second two powers that are almost equal mutually, we put them together as some kind of average, and the other terms we do not take into account. So we do go some way, sorry, beyond this simple, naive expression at dimension 6. In our operator product expansion, we will not go further because very little is known for dimension 8 terms, etc. So we will truncate here, hoping that OPE has some kind of convergence. We know it's not convergent, but kind of asymptotic behavior where we can cut it reasonably at some here at dimension 6. Now, these are the sum rules and the look at the OPE, but the operator product expansion of the Adler function is very closely related with the renormalon structure, infrared renormalon structure of this part of Adler function. In fact, these terms here are reflected in the renormalon structure here. I will go into that in the following, that we will construct certain renormalon structure for dimension 0 part of Adler, which will reflect this information that we have here, this and this. Now, if we look now at renormalon-motivated construction of Adler function dimension 0 part, it has in principle, yeah, we can use power expansion, perturbation expansion. Kappa is simply a renormalization scale parameter. It's mu squared over q squared, usually of order 1, or it can be taken 1 often. And this expansion of the Borel transform of this is this. And how do we get the renormalon structure of dimension 0 Adler function? We look at the Borel at this transform close to u equal 2, u equal 3, etc. And what we get is that close to u equal 2, it has a singularity of this part, this type, and this is already less singularity, one power of 2 less, etc. And at u equal p, let's say this p is 3. First of all, this singularity here would reflect itself in the power expansion, in the operator power expansion here in this term, dimension 2. You have here this 2, yeah, u squared 2. Well, these terms here will be connected with the singularity of Borel transform of this at u equal 3. You see here. That means if this p is 3 here, this is the second infrared renormalon. It has specific powers here, namely such powers that when we evaluate through Borel resummation the d equals 0 part, we should get, I'm trying to say something in advance, we should get the q dependence here ambiguous, yeah, because the Borel resummation has some ambiguity, and q squared dependence of this ambiguity should reflect these terms and these terms, which means we should get the same q squared dependence of ambiguity from Borel resummation here of this evaluation through Borel resummation, the same q squared ambiguity from u equal to singularity as this, the ambiguity in integration, Borel integration around u equal 3, we should get this dependence. The idea is that the ambiguities here and the ambiguities here, they combine and cancel. So the whole thing here, which is unobservable, has no ambiguity in principle, at least. Okay, so now for p equals 3, we know what these powers are in order to get the same q squared dependence of ambiguity as OPE there at a dimension equal to 6, which is 2 times 3. This is here 3 then, which corresponds to dimension 6 in OPE. Now these powers here are 1 minus gamma, some complicated expression, but this gamma 1 is the effective leading order anomalous dimension of the dimension of this operator appearing the OPE. Let's say what we have here, for example, this here is anomalous dimension divided by this constant beta 0, one constant. And this is another anomalous dimension divided by beta 0. These anomalous dimensions here enter the powers in the singularities. P equals 3 here would be powers here. Enter these powers, how strong the singularities are of the Borel transform at the corresponding infrared renormalon point. Here, for example, this is the same. This is this power that in OPE appeared. It is here now. Of course, these powers are not equal. This is not here. It is 1 minus this. And in addition to that, there is some combination of beta 0 and beta 1 functions here, which comes from the effect of RGE running of the running coupling of QCD. I'm just trying to say here some facts that are known, but it's not not easy to show, but that's how this works. Now, beta 1 and beta 0, these are this universal beta coefficients here, number of flavors in our case at the energies we are looking at up to 2.8 GeV squared, we can take 3. So beta 0 is simply 9 divided by 4, which is 2 certain numbers, and beta 1 is again certain numbers. So there are here certain numbers, and this P is here 3 now. Yeah, if P is 3. The other important thing is that 2 minus U has this kappa simply 1, that is an effective leading order anomalous dimension for dimension 4 operator is not there, is 0. This is 0 here. So we have simply 1 here. And we can see that, of course, because there is no K2 here, no K1 here. There is no leading this effective anomalous dimension there. This anomalous dimension tells us how in the leading order these condensate operators would run under the RGE evolution. Okay, now the requirement that the Q square depends of the dimension terms in OPE of Adler function is the same Q depends as that of the renormalon ambiguity of the inverse Borel transformation, Borel integral. That's what I mentioned before. For example, this ambiguity, when we try to now, let's say that, we have these Borel terms of this form, and we want to now calculate the corresponding D, but just looking at these terms. How to get this? We have to make the integration here over U, and this is the coupling here. But the problem is this obstacle of integration, because when we integrate along positive U, when we come close to this P, in our case, this P of interest would be 3, we don't know how to avoid it. We could avoid this pole by going upward or going downward. If we go above the real axis or go down the real axis, the ambiguity is proportional to imaginary part of this. This is typical ambiguity. We don't know, how to evaluate this, or one way or another, and the difference between different recipes is proportional to this. Now, it turns out that these integrals with these powers that are mentioned, here, these are these powers here. What do we get? We get, in fact, that this part of imaginary part are these functions. If you look at here, that's exactly now if P is 3, and this is this Kj, is exactly what you see here in OPE. This is 1 minus this K2, and this is 1 minus K1, where K1 and K2, okay, it's the same. This is, you see here, this is the effective leading order anomalous dimension that appears here. it's the same. Yeah, that is, now we have this relation now between the dimension 0 and what is happening here, and also here and here. There is something more in the Borel transformation, that we have also so-called ultraviolet renormalon poles for the Adler function. We know that they exist there. These are the singularities when u is -1 or -2, negative ones. They do not represent any obstacle to integration here, so they give no ambiguity, and they do not reflect themselves in the OPE in this way. But still, if we want to construct Borel, a model for Borel transform of Adler function in dimension 0, we have to include at least the first ultraviolet renormalon poles. So the other thing now is, sorry, we can go, here. We will assume here for the ultraviolet renormalon poles that these terms here are, these indices here are basically the same as in large beta 0 approximation. That is, we have no such problem here with anomalous dimensions, yeah, for ultraviolet poles. We don't know that much about this power, so we take large beta 0 approximation here. That means it's double pole at u equal -1. This is the first ultraviolet renormalon. The other thing is now to think about a reorganized expansion of the dimension 0 Adler function within this renormalon-motivated Adler function. In fact, instead of powers, we can use logarithmic derivatives of the coupling. Now, more logarithmic derivatives gives us combinations of these powers and higher order corrections. Now, in the first approximation, logarithmic derivatives are equal to the powers, but beyond one loop, they are not. So, and thus, we can always reorganize the power expansion in the expansion in these logarithmic derivatives, because they are connected, logarithmic derivatives with powers 1 to 1. So once we do that, the coefficients now are tilde here in the logarithmic. And in the powers, when we have power expansion, these are dn without tilde. Just to remember notation. Now, we can play with the following. This is now interesting. If we say that, yeah, we do this expansion, but now we replace this formally by powers of A. We can thus construct Borel transform with tildes, which is Borel transform of an auxiliary quantity that is not Adler function. Only in one loop approximation is equal to Adler function. Yeah, but we know how to do it, because if we know all the coefficients dn, we
Are we?
as if everything were one loop. That means that Borel transformation under the change of, under the change of renormalization scale is simply like this. Kappa is mu squared over q squared. It's simply like this. It is like one loop approximation, but this is exact here, which means that suggests that in order to construct the Borel transform of d tilde, not of d, but of d tilde, this is dimension 0 auxiliary quantity, we would have these powers the same as before for B and D, but with beta 1 replaced by 0. Why? Because beta 1 is two loop effect of the running of coupling, but here we have as if it were one loop running coupling. Yeah, it behaves as if it were one loop. So this suggests that these powers, sorry, these powers here, we cut out and we say, okay, just these powers remain. Beta 1 is 0 because these are effects beyond one loop, two loop effects of running. So we just suppose that Borel of d tilde has such terms without those beta 1 over beta 0 effects in the powers. Now, still, K1, K2 are these non-integer powers, and 2 minus 1 has just 1, and these are non-integer powers. K2 is 0.8 roughly, K1 is close to 0.4. And these are the ultraviolet parts. So if we do that, this assumption, it's maybe, it looks like conjecture, but we can do the following. We know that once we have this, each such term would generate the corresponding dn tilde. By knowing dn tilde, we can calculate through these relations all the dn. Having the dn, we can calculate b of Adler function, corresponding Adler function, if b of d tilde has these forms. And it really turns out numerically, this has been shown 3 years ago, I showed in one paper, that the corresponding terms exactly get these terms in addition, yeah, in comparison to this without here. That is really, now when we go from BD tilde to BD, we obtain the powers that are theoretically expected. These are exactly the powers that are, look here, theoretically expected. These are the powers with this. So it is somehow, this is a confirmation that this is the correct ansatz, that the renormalon structure of BD tilde is somewhat simpler, especially for U equal 2, the first infrared renormalon. And for this also somewhat simpler because it doesn't have these effects of two loop running, beyond one loop running of coupling. Okay, so what we do is, sorry, now for B d tilde, now this d tilde is auxiliary quantity of Adler function at the dimension 0 of the entire Adler function, but auxiliary this quantity corresponding. We do the following ansatz. We say, okay, these are the terms with the first infrared renormalon. This is added because this is some kind of correction. I will not go into this, but it's some kind of further correction of the first infrared renormalon that always can appear. And the second infrared renormalon with this corresponding kappas, and the first term of the first ultraviolet renormalon. So we know that the structure is there. The first two infrared renormalons and the first ultraviolet renormalon are here. Now the question is, okay, this alpha tilde can be calculated. It was calculated by me about 3 years ago. And these are 4 coefficients here in this ansatz. These are residues, yeah, residues at the renormalons, and a rescaling function. This is some kind of rescaling function like, okay, 5. Now, these 5 coefficients can be obtained if we know, for example, in this expansion, the first 5 coefficients in the expansion. In fact, we know exactly the first 4. This is 1, and the other 3 coefficients we know. The 5th coefficient, which is D4, we do not know exactly. But there are many estimates of this 5th coefficient D4. In fact, effective charge method, but also other estimates give us these values, roughly 275 plus minus order 60. I mean, I put this because one estimate that differs from most of the others gives us this value. So we will take for D4 these estimates, 275 plus minus 63, and D2, D1, and D3, the exactly known values. So we know in altogether 5 pieces of information, which gives us then these 5 parameters here in this ansatz. So we get this. When D4 is this, we get these values for the parameters of the Borel transform of auxiliary Adler function. And when D4 goes down, they do adjust themselves. So this will be our central value, for example, and then we will vary. Now what we do get once we have this is the following. The expansion of this will give us all the D tilde values. We know exactly now the terms up to D4 tilde because we know the coefficients up to D4. So we know all the coefficients also up to D4 tilde, but D5 tilde, etc. we don't. But once we have this with the fixed parameters already, we get all the Dn tilde, we get all the predictions of the coefficients Dn, this coefficients of the expansion, all the other of the expansion. So this model gives us, in fact, information about higher order coefficients, estimates of higher order coefficients of the Adler function, dimension 0 part, which is now here. For example, when D4 is this, these are Dn, when n goes, and Dn tilde and Dn. Look at 4 is 275. These are exactly known. And these are the other terms here. We see that the effect of ultraviolet renormalon is small. Although this renormalon is close to the origin, its residue is always small, 10 to the minus 2, while infrared residues are stronger. So they were more important at smaller n. More important, now at the end, the effect of infrared renormalon for the first time comes at n equal 10, because ultraviolet renormalon is responsible for alternate signs of dn when n increases. But with dn tilde, it is to be seen already at 4th order. So this is much more, okay, it has different sensitivity to renormalons. Now we go back to specific sum rules, because we now have in these sum rules all the coefficients in the expansion of this in principle. We would like to know what is this, what are these terms, and what is the value of the running coupling that appears here, but appears also here. What is? So we would like to know it by looking at the sum rule, this sum rule, and see if we can get all the information of the about the coupling that is here now, and the condensates. And what we do is we apply now the sum rules with the following weight functions, or Borel-Laplace transforms in the sum rules. Weight function is exponential. This is typical Borel-Laplace. Here, this is double pinched, which means when q squared is negative minus sigma m, this is really suppressed. So we do not have duality violations. This large G, which is integral of this, is slightly more complicated, but it's also a combination of exponential functions and powers of q. So when we go with that into the sum rule and take into account the dimension 0 part that was there, that the renormalon model generates, we get the following. The experimental part of the sum rule, it's this omega experimental, and here are exponential functions. The theoretical part is, this one is coming from term 1 of an Adler function. This here, all this is a contour integral on the radius sigma m, which is 2.8 GV squared, of all these large G. And this is our Adler function, where we generated by renormalon model all those coefficients of expansion. And these are D4 and then D6 terms. D4 term is relatively simple here for Borel-Adler function. It's proportional to 0.4. And another thing is, of course, that I should emphasize, Borel-Laplace transform have another parameter that is in fact free. It is a scale parameter. M squared is a scale energy square. We can vary this in complex plane. So Borel-Laplace transforms give us tremendous liberty to vary the weight functions, to have a continuous set of sum rules which we can apply. Yeah, it is different from the usual finite energy sum rules. So what we have here is now all these integrals here, where m squared is arbitrary, in principle arbitrary. It shouldn't be too large, of course, for reasons of that the non-perturbative behavior is not entirely known, but it could vary up to the order of 1 or 2 GV squared. Now, here dimension 6 is a bit more complicated, because here we have these couplings running also, but that's how it is. And we can also use finite energy sum rules, where the weight functions have no additional m squared parameter, they are fixed. Yeah, 2, 0 and 2, 1. We use this n here is 0 or 1. The experimental part of these sum rules with 2n are given here. And sorry, I should now, yeah. As I said, the dimension 0 part here in the sum rules, where is this here? It is here. Okay, dimension 0 part in the Borel-Laplace sum rules is here. We can evaluate this one now by using fixed order perturbation theory, and we can go to higher orders because our model gives us estimates of these coefficients. So up to certain n truncation order, we do this expansion and we go into the contour integrals. That is fixed order perturbation theory in these contour integrals expands this A at sigma m A phi, where phi varies between minus pi and pi, around, we Taylor expand around phi equals 0. Yeah, this is the space-like point here, positive, and we do Taylor expansion in powers of phi here. Yeah, that's the fixed order perturbation theory. I will not go into details, but another is fixed order perturbation theory using logarithmic derivatives. That is, dimension 0 part on the contour of Adler function can be also expressed as the logarithmic derivatives. Equally, logarithmic derivatives can be re-expressed at I phi as logarithmic derivatives when phi is 0, yeah, and higher logarithmic derivatives. And we always then do truncation at certain order, a logarithmic at n truncation. And here, certain powers up to n truncation. So these are two versions of fixed order evaluation of Adler function. In fact, we cannot do here complete resummation because this sum is divergent. So we always have to cut it, yeah, as it's truncated. Fixed order perturbation theory has to be truncated at certain powers. We can also do the other method of dimension 0 part, which is inverse Borel transform, but now with the principal value to avoid this ambiguity, to fix the ambiguity or renormalon ambiguity. That means that dimension 0 with principal value, we calculate the singular part of the Borel transform of Adler function. Now, singular part, I will not go into details, but what we have here are these powers that I mentioned. like these terms are there, these terms, and these kind of terms are there, and these corrections here. We include one, in some cases, two terms of these corrections and cut here. That is, the singular part here is not exactly full Borel, but the most singular part. What remains is Borel of Adler that has almost no renormalon singularities. And that part contributes here to a simple polynomial or truncated power expansion of correction, correction term here. And this one here has the expansion coefficients which have no renormalon growth. They should behave in a very controlled way. So if we increase here number of truncation, the results should not change. Theoretically, it is expected should not change much because this series has no renormalon type of now divergence, in powers of A. Anyway, but also here we have to do truncation, and we don't know where to make it, at which power of A to make truncation in this part of the correction term. So these are the methods. In fact, there are two types of fixed order perturbation theory method and one with Borel, inverse Borel transform with principal value. We use, as I said, V plus A channel of ALEPH. What we in practice do is we, in some rules, we equate a real part of Borel-Laplace. Imaginary part, okay, it could also be done, but we equate the real part. And what we do is we use m squared in the Borel-Laplace in an entire interval between 0.9 and 1.5 GV squared. For phenomenological reasons, m squared absolute should not be too small or too large. Now, the other thing is that m squared will be taken along 3 rays in the first quadrant of m squared. These are the rays here. And we on each ray, we use 11 equidistant points. So what we do here is we make fit between experimental and theoretical parts, and these are the deviations or experimental uncertainties, squaring this and doing sum over the 3 rays, which is altogether 33 terms. So it's a very strong condition that we want to minimize this. That is, we want to have such alpha S and such dimension 4 in dimension 6 condensates that this is really small. That is, that these theoretical values and experimental agree in a large important part of the complex plane of m squared. When we do this, you can see, for example, that it works very well along what we get when we minimize this. Now, just along the ray pi over 6 for m squared, and this is absolute value of m squared, real part goes like this. Now you can see this small band. This band is experimental band. It's very narrow, and our best fit theoretical line is in this entire interval quite well within this, although very narrow band. So it works very well. In the end, what we get is with this fitting, how do we now fix the power, the truncation index? We look also for each truncation index, we do minimization and we get certain alpha S and certain condensates, and then we calculate these two momenta, O to 0 and O to 1, which are these fixed finite energy sum roots, and we look how they behave when we increase the number, the index of truncation of each method. This is tilde FO, this is FO, this is principal value. I included here contour improved, but contour improved is not taken into account in our analysis because it does not respect the renormalon structure. What we see here is that in a certain number of truncations, they get stabilized, and they get stabilized for each method A21 and A20 at about equal number of truncations. In fact, the stabilization we get for fixed order around 8, nt is equal to 8, for FAO2 at 5, for principal value at 5. We can see also here, for example, here at roughly 5, this becomes very stable, but then, okay. And for these values, this will be the central cases, we get this alpha S at m tau for the three values. The uncertainties we get from are experimental, which are very small. It has to do with the fact that ALEPH data are quite precise and they give us very narrow bands for Borel-Laplace transforms. So these experimental are small uncertainties, but the uncertainties theoretical, which is due to the variation of renormalization scale, or this variation of D4, as I said, D4, we don't know exactly what it is. We took it 275 plus minus, I don't find it here, 275 plus minus roughly 60, no? So these are theoretical uncertainties, and if we vary the index of truncation another. So what we see is that in this analysis, the experiment is ahead of the theory because the uncertainties, theoretical, are clearly larger than experimental one. When we combine that in squared, we get for each method of the three methods, this predictions for alpha S, and they are not so far away from each other. That's also interesting. They are not so far away from each other, and the total ambiguities are also not so large. Yeah, total uncertainties. If we now okay, here are the results in this method, but also the condensates. The uncertainties in condensates are larger because when we change NT, this vary. But still, there is even some prediction for this. This is dimension 6 effective condensate, which is this combination here. This he squared, which is the sum of 33 squares here, is very small in all cases of order 10 to the minus 3 in all three cases. So the fit is very good. And the arithmetic average of the three methods gives us this value for alpha S at m tau, roughly this. And if we go to the RGE to mz squared, we get this value. The uncertainties are relatively not that large. We can also see the following, that if we took in our method, instead of the improved dimension 6 contributions, just a large beta 0 effective leading order anomalous dimensions, that is when these anomalous dimensions are -1 or 0, which is different from, this is just large beta 0. In that case, as we showed in our previous paper, the value of alpha S is larger, is somewhat higher, and alpha S and MZ is 1191 central value, while here is 1184. On the other hand, when dimension 6 operator product terms are taken completely as non-running, that is, all the anomalous dimensions are taken 0, as we did in the first paper, and as most people do, this is the naive OPE. What we get is somewhat lower value of alpha S, and this is here alpha S at mz squared, but not far away, in fact. If we took just number of truncation, always 5, you notice that in FO, our number of truncation was 8. If we took 5, then only fixed order, that is, if we do not take into account any extension of Adler, because Adler function tells us what are the coefficients beyond truncation 5. Up to truncation 5, we have the ends. So if we took everything 5, the result would change a little bit. Will go down a little bit to 3171, and alpha S at MZ would go from 1184, central value 1183. So it's in fact very little. This extension of Adler function did not affect significantly our analysis. It is also interesting now that our analysis gives us values which are slightly higher than world average of the lattice approaches, which is 0.1182 plus minus 0.008. But the world average of non-lattice approaches give the central value here significantly lower, 0.1175 plus minus 0.010. So it's interesting, our approach is non-lattice, and it gives the result that is close to world average of lattice and significantly larger than the world average of non-lattice results for QCD couplings. With this note, I would like to end this talk. Sorry for the delay. Here are some some comparisons from tau-decays. Our result is here, while these are some previous results, by different methods. Yeah. Okay, with this I end my talk.
Thanks, Gorazd, for this very nice talk. Does anyone have any question?
Yes, I would like to ask. Well, thank you, Gorazd. It's a really fine analysis. I mean, with all subtleties, it's beautiful. But I remember at the beginning of your talk, you mentioned that as a second filter, you wanted also to take finite energy sum rules into account, and not only Borel sum rules. In which part of the analysis did you go through the finite energy sum rules? Yes. Or I missed the point, but I was trying to understand.
I almost ran over this point. Here I was talking almost all the time about minimum square fit for Borel-Laplace. Now, as for each number of truncation in our method, we get a different now value of fit. So we get a different alpha S and different values of somewhat different values of condensates. Now the question is, which number of truncation, index of truncation is the best, so that we don't have these ambiguities here. And there we used A20, A21 finite energy sum rules. We used now at each NT, this is NT here, at each NT, we used the alpha S and condensates obtained from this fit of Borel-Laplace, where we use this NT. And then we calculated for this each NT A20, A21. Now, these bands are experimental bands by ALEPH. So we get all these, for different NT, we get the finite energy sum rules well within the experimental bands, which is to be expected because we got the results of alpha S also from ALEPH rules, but from different sum rules, Borel-Laplace. But now we looked, maybe this is somewhat arbitrary, but what we looked at is how this A20 in one specific method, let's say the method fixed order. We look here, this is fixed order. It goes down, 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 and then it gets here stabilized between 7, 8, 9. And then it's hard to see, but then and here also, A21, fixed order, it goes down, it it reaches a stabilized stationary point roughly NT8, and then it goes again up. This is even more so in can be seen in FO tilde, that for example, it stabilizes somewhere here between 4 and 5, and then it becomes more and more violent, less predictive.
Yes.
Principal value, in fact, is I find it's amazingly stable. Principal value, amazingly stable. It doesn't matter almost, but if you look very carefully, you see that around at 5, NT5, it's almost constant. It doesn't change when we vary 5 plus minus 1, it's almost the same result. So that's how we fixed number of, how we used this as this additional filter to fix the number of truncation in the method.
Thank you. Thank you.
Thanks. So is there any other question?
May I ask the very
Gorazd?
No.
I'm sorry.
No, go. Bastian, go.
Okay. I have some general questions. For instance, is it possible to extract alpha strong coupling, the strong coupling of QCD from other particle decays, a part of this tau, for instance, in the neutron, which has similar masses? Is there another possibility?
Yes, there are definitely. You can get also, for example, from upsilon decays or some somewhat more heavier particles. The good thing about tau decays, especially the ALEPH data, is that it has high precision. I would say that ALEPH data is the highest QCD precision measurement at relatively low energies.
Yes.
So ALEPH data are like some point of reference to give us warnings about what is happening when we approach the non-perturbative sector. And as you can also see, these tau decays are very good because experimental, I mean, the theoretical uncertainties cannot even compete with this. And as far as I know, other experiments are not so precise, with other decays, are not so precise as this tau semihadronic strangeless decays.
And Gorazd, what about electroweak quantum corrections in this type of processes?
There are electroweak corrections, but they are here eliminated. I think they were calculated also by Sirlin and Marciano, but they are taken into account indirectly. Why? I didn't go into details, but this omega here, these are pure QCD effects. In this, let's say, what is this omega? It's here. This is measured by ALEPH, but what is measured by ALEPH is not just this. This is the QCD part, but there is also electroweak part. It was subtracted from here, but it is known to a high accuracy.
Thank you. Is there any other question? Maybe Marcelo, you have something to comment?
Yes. At some point, you said that you haven't used the contouring proof perturbation theory because there was a problem with the renormalon cancellation. Can you comment. Also, I missed the point. Sorry, but
yeah, this is still a point of controversy at the moment in the community, especially tau-decay community. But this was already first raised. Warning about this in this work by Benek and Yamin 2008, where they show that even in large beta zero approximation for R tau decay, which is basically fixed finite energy sum-Rolls for A21, they showed that contour improved model, when you truncate it, you are cutting through strong, possibly strong renormalon effects, and this truncation of contour improved sum does not respect the renormalon structure. You are cutting through it. That is, that one part remains outside and one inside. I cannot really explain this well, but
okay, no, but now I see
that
what you are thinking about. Okay.
Yeah, even if you take more terms in contour improved, you should expect that you have large uncertainties there, because you will always get some large effects of renormalons that are not resummed. Contour improved part resums some part and then leaves out other parts. And what we have is that these parts, in fact, have strong cancellations. And now, if you have strong cancellations, when you truncate, your method should take these cancellations at each truncation order into account, plus and minus. What contour improved does is it takes one plus, for example, there, but it cuts out the minus at the same order.
Okay.
So it makes, and we can see even here, for example, in our analysis, we just looked, we knew that it does not respect these renormalon structures. Just look here, alpha S is completely off the chart,
yes,
in comparison to these others, completely off.
Yes, thank you. Yes, thanks a lot.
Thanks, Gorazd. So I think it's time to finish. Thank you very much for the talk, and see you all next week, and we will send you the information for the next talk. Thank you very much. Have a nice afternoon. Bye-bye.
Thanks, bye.